let's start introducing Professor Caio Lewenkopf. He got his bachelor's in 1986 and his master's in 1988 at USP São Paulo. Then he went to Germany to get his PhD at Heidelberg in 1991. Then he did a series of postdocs, one being the Max Planck in Heidelberg. Then he went, this in 92, 93, he went to National Superconducting Cyclotron Laboratory at Michigan State University. He was probably freezing his butt up there. Then he went between 93 and 95, he went to University of Washington in Washington State, USA. Then he came back and got a postdoc at USP, 1995 and 96. And then from 1996 to 2010, he was at UERJ in Rio de Janeiro. And during this time, he was a visiting scientist in Strasbourg, 1999, a visiting professor in Harvard in 2007, an associate director of CNPEN in Campinas, 2008 and 2009. And from 2010 to now, he has been at Universidade Federal Fluminense in Rio de Janeiro. Niterói, Rio de Janeiro, state of Rio de Janeiro. So today he's going to talk to us about entropy production in the electronic transport in nanoscopic systems. So Professor Caio, thank you very much for accepting the invitation again to talk to us. It's a pleasure to have you here, and the microphone is yours.
Okay, thank you very much, Georgie. It's a pleasure to giving a talk. I think I'm giving too many talks at your program, so I think I already gave one this year, but I was confused. It was last year.
It's always a success. It's always a success.
Yeah, well, it's good to have friends. I actually then changed a bit the main topic. The last time, I guess, I was talking about topological insulators. And this time I'll be speaking about entropy production in electronic transport in mesoscopic systems. No? The colloquial title would be quantum thermodynamics, which is more catchy, but this is more specific, and since most of us are working in the condensed matter community, I think this title is more adequate. It will describe more precisely what I'm going to discuss today. So in a snapshot, and I have to apologize, when I go to the presentation mode, my mouse disappears. So I'll be presenting this way. I hope it's not too bad for you guys. So in a snapshot, the main contents of the talk, or at least the motivation, is captured by this beautiful drawing. And the idea is the questions that I'm going to ask are related to the following. Suppose that I have a left and I have a quantum system, and these discrete levels are to be representing the quantum of the system. And this could be a quantum dot. It could be something else, like a 2D system, could be anything which is where quantum phase coherence is sufficiently long that is influencing the final results of your measurement or your theory. So the idea is that if you have, for instance, a quantum dot, a finite system, finite conductor here indicated by yellow, and you attach it to left and right leads, two contacts, and you put, for instance, a bias, a difference in chemical potential, or you drive the system by just putting a thermal gradient, a current will flow. Electrons will move from one reservoir to the other and pass through the system. And this process is irreversible because you apply the bias. The system is out of equilibrium. And the question that I want to ask is, what is the entropy production in such a situation, right? So can we compute, can we calculate, can we measure the entropy production, the heat, eventually the work that is act upon the system, things like that? And this is the subject of today's talk. An answer, since I'm giving the talk, I propose an answer, and the answer is positive. And I'll show you how at least you can formulate theory which is consistent, is self-contained, and is, it's very plausible. As far as the experiments go, then things are more complicated and tricky. And if I have time, I will discuss some of it. So as a colloquium, I would, instead of going directly to the main thing, I'll divert and speak about engines, macro versus nano worlds, right? And well, we know since physics 102 or thermodynamics, right? All these things about heat engines, Carnot cycle, efficiency, and the bounds that a system is, a thermal system is subjected to when one thinks about how much how good the system can perform. Now, one of the challenges of the field is to think, well, suppose that I make these guys, these classical things, very small. So small that first you violate one of the big things in thermodynamics, the thermodynamical limit of large number of particles. You can still be classical. And then are these laws still applicable? Well, probably as an average, but you have to live with the fluctuations. Now, if you go to the quantum world, right? So are these laws still valid? And that's a genuine question, since these are laws, right? So there is lots of evidence that it works perfectly well in the classical limit, macro world. But as you go to small systems, very minute, nanoscale, then the reasons, well, then there is no things to back you up, right? So, and the field has grown very fast, and there are many interesting questions that have been addressed by different groups. And before the pandemics, a long time ago, I used to go to the conference, and I was always very excited by all these topics that have been discussed. And so one is still very hot, is thermalization. When and how isolated systems thermalize, many body interactions, quantum systems, and well, there are lots of papers coming up every week on that. Quantum fluctuations of thermodynamical quantities are just the realm of this, and I'll address some of this in this talk. So there are people interested in time arrow, in entropy, including some Brazilian groups. And they are performing experiments and trying to understand if there is time arrow and all that, and if the quantum world helps you with this understanding. So I'm not going to talk about that. There is an interesting connection between thermodynamics and information entropy, and I'll explore some of these ideas here at a very simple level. But people are using these to understand effects in quantum antibody systems and related effects in entropy production. And this is very exciting. So obviously, when you talk to people that have more practical minds, they're interested in efficiency of quantum heat engines and devices. And there are many interesting experiments out there even on photovoltaics, optomechanical devices, these two finite time operations, like you have to compete with level crossings. I mean, if you're not a diabetic, then things tend to excite and be irreversible, quantum refrigerators. And if you Google on that, you see lots of interesting works. No? And there are all these are related to also to experimental proposals to measure the energy exchange by one of these minute, simple systems. And starting with the Cooper pair boxes, People have evolved to cold atoms, and there are lots of things going on in the cold atom community, and also in quantum dots. But in quantum dots, things are evolving very slowly because it's hard. It's hard from the experimental point of view. Okay, so nowadays, well, so since George introduced me, I'm an old guy, and I'm always very impressed by the tendencies of the new era. And nowadays, even if the field is very young, people already write reviews. So everybody writes a review right away just to to set the stage. And amazing enough, there is a review on quantum thermodynamics, electronic systems, although there is very little things, very little experiments on that. And this review was written in 2015. I mean, 3 or 4 years just after the first experiment. But it's a nice review, actually. So progress in electronic circuits related to that is slow, and it's still sort of updated. And I put this view graph here just to illustrate what is the kind of experiments that people do, right? So the idea is that basically what you got is a quantum system, right? And whatever you do, a measurement or drive is of a classical nature, right? So the system is quantum, the drive is classical. And then if you're interested in electronic systems, then actually you're interested in the electrons, right? And typically people have analyzed tunnel junctions and things like that. You drive the electrons and you see as the electrons tunnel out of a barrier or out of a system. And basically you watch this with very closely, and you try to infer all the information, gather all the information you can about the energy transfer, the rate that things happen, etc., etc. And obviously, since this is quantum, phonons are bad for you. So typically people try to do these experiments, at least in electronic circuits, at very, very low temperatures, so that you guarantee that the quantumness of the system is still preserved. Okay, so this is the setting. I don't think I'm describe this. Yeah, I'll just flash it. These are the first experiments that people have done in single electron boxes, quantum dots or tunnel junctions, and basically they were just verifying things which transcend a little bit of the focus of that, and things like Jarzynski equality and properties out of equilibrium. The issue is what is really quantum here, right? So because you measure electrons and the system is discrete, etc., but all this has nothing to do with interference and quantum coherence, etc., etc. But nonetheless, these are very remarkable experiments. They inaugurated, so to say, the experiments in quantum thermodynamics in electronic transport. So just for the record. Okay, so the outline of the talk is that I will basically start defining the problem, tell you about thermodynamic limit, nanoscale, strong coupling, classical versus quantum aspects. So if I get these messages true, then I'm already very happy to define what are the challenges in the field, for at least for us. And then the second thing is I'll tell you more about entropy production, which is actually the main topic of the system. And then I'll go to the these details of what I do. I introduce a model, and I use theory that many of you are already familiar with, but I use this theory in another context to explain how you can actually model and calculate things in quantum systems. Okay, so let's start with the basics and address the idea of discuss a little bit the idea of thermodynamics of small systems, right? And actually, it's very interesting. I found out some time ago that this guy Hill was already very interested in this problem, and he was interested in this problem in a very general perspective. What do you do in thermodynamics when n, the number of particles, is not that large? And actually, there are these two books in Dover in '64. So that means that he was working on that much before, because when a book is published by Dover, it already has a long history, right? And interesting enough, in the first issue of Nano Letters, he wrote an invited paper on let's say thermodynamics of nanoparticles. That was in 2001. And okay, so but what is this all about, right? And what this is all about is very nicely captured by this figure here. Suppose that you do an experiment that people do nowadays. You have RNA strain, and this is basically you trap with a pipette, and it is sort of coupled to a system, like a laser trap, and you want to stretch and do things to it, and you are dealing with a system which is large, right? It's very large, but still not 10 to the 23 particles. And basically, it's large, but the regions where you connect the system, where you have a coupling of the system to the bath or the coupling to something else, they are significant and comparable in size with the system itself. So it means, I'm talking about classical systems still, right? So let's say this is in room temperature or something like that. So it means that if you want to write the energy of the whole system plus environment, it's very convenient always, and this is the first step we do in StatMech, to introduce a partition where you write the energy of the system, the energy of reservoir, and the energy of the coupling, right? And normally, when you open this statistical mechanics books, the first thing that people cross out is this coupling, because they say, at the interface, there are very few particles, or the energy stored in the interface is small. But when the system is not small, when the system is small, then you cannot do this operation. Okay, so this is one thing I'll discuss more. And this is what is meant by strongly coupled systems. But let's stick more to the macro versus nanoscale, right? So suppose that I have at a macro scale, I have a rubber band and I keep pulling, right? And I keep deforming the poor rubber band. So if it goes back very nicely like a coil, then it's fine, it's reversible. But suppose that I keep distorting and destroying the rubber band. So I begin at equilibrium, I stretch the system, I do some work, and it goes back to equilibrium, right? And to some extent, it's irreversible because I'm degrading this guy. And in an RNA strand, it's more or less the same. So I can pull and push, pull and pull back, etc., and perform a cycle on that. Now, never go back exactly to the same configuration. It's already clear here, right? So you have fluctuations. And the idea is that if you have a macro system, then basically, what we learn is that there is a work, there is free energy, and there are all these things that you compute, and these guys don't fluctuate, or at least the fluctuations are on the scale of 1 over square root of n, which is a formidable number. Whereas if you have a small system, in average, you actually will retain all the nice relations of thermodynamics, but these guys have a distribution. And sometimes crazy things will happen, and you even will violate some laws which are meant to deal with very large systems. This is an effect of fluctuations. This could be rare events or could be not so rare, right? And this is classical. And then let's go back to track, because we want to address equilibrium production and non-equilibrium processes. So, this is my last introductory slide. I beg for a little bit of patience. Very soon we'll get to the main thing. So, entropy production is something that people have been worried for a long time, right? And even in non-equilibrium processes where this is expected to happen, at the very beginning of StatMech, these ideas were already there. And I'm talking about Boltzmann, nobody else than Boltzmann, who formulated the whole business, this transport equations and the whole concept of basically statistical mechanics, if you want. And very early in the game, he was worried. Well, this is put in the modern language, the ideas that were originally formulated by Boltzmann, but never mind. So he was worried about the time evolution of distributions of particles in phase space, right? And using classical mechanics, if you wish. And if you have a system which evolves using classical mechanics, and there is nothing else than external forces, single particle forces acting on them, then the Liouville theorem will say that, well, if you have a snapshot in phase space here, then as you evolve in time, then you keep, like the volume in phase space constant. But reality is a little bit more complex, and the particles interact, and this is a many-body system, and you have to go beyond the single particle description. So eventually, particles which are outside this volume in phase space might end up inside due to collision. And some of the guys which were inside, they might go out because also collide. And there is so Boltzmann envisaged that, and he understood that you need to take into account these collision terms in order to describe the time evolution of this system. And more than that, he said, well, I cannot really describe all these particles individually. I have to make some cross-graining, take some averages. And that was the basis of his famous Boltzmann equation, right? So in the absence of collisions, this guy is zero, right? The total derivative follows the Liouville theorem. But if you're interested in the distribution of particles in phase space, then there is this collision term. And actually, very early in the game, he ended up doing something else, which is a very nice thing. He understood that this collision term has something to do with some, well, this is a modern formulation. I put some matrix element, but it's a result of collisions between these particles. You can even describe them classically. And he postulated this H function, which I'll call S is equal to minus H. And Boltzmann's H theorem will say that during the evolution of a given system, this H, the derivative is always zero, always negative, except at equilibrium when it's zero. So if I put a minus here and call this minus H entropy, then it tells me that during the evolution, you actually, the reversible processes will make the entropy grow in this form. And this is the form we use, actually. And in equilibrium, when you go to equilibrium, this guy is zero. And this implies, actually, and you do some little algebra, that F acquires a shape which is known as the Maxwell-Boltzmann distribution. Beautiful, beautiful piece of work, which is almost 150 years old, right? And now we are dealing with that in quantum mechanics. So that's the new thing. In quantum mechanics, you have this quantum kinetic approach, right? So there are many reviews on that. I didn't contribute to this issue. And basically, if you deal with the non-equilibrium systems, it's usually good if you formulate things in terms of Green's function. And this here is, for instance, the non-equilibrium Green's function called G Lasser. And already in the 90s, 80s, people understood that you could construct some local entropy density in terms of these quantities, and actually compute things when you do this quantum kinetic approach, and you eventually will end up with some continuity equation, and you can understand how entropy is produced by this collision terms, etc., etc. The problem here, and why is this not really satisfactory for the things we are dealing here, is that, as you can see, this guy is, by the end of the day, is a semi-classical quantity, right? And all this quantum kinetic approach is semi-classical. And at some point, you have to take Wigner transform and do things with the Wigner transform and throw away some terms that are real, the quantum corrections. And so there is a theory, people understand how this dissipation processes in conductors, in the bulk, but all this is formulated in a semi-classical form, right? Going to smaller systems makes us, opens the possibility that you can actually address this issue in full, right? So you are not really going to the semi-classical. You are not really interested in bulk properties, and this is what I intend to describe in the last half hour that I have. So this was the end of the introduction, and this is the kind of problem that I'm interested in. Suppose I have a quantum dot or a conductor, which electrons that are confined to a certain region in space, there is a source and a drain, and electrons enter and exit the system here, and there is a coupling, right? So that allows the electron to enter and exit. For all purposes, I'll consider this quantum regime where the quantum coherence length is much, much larger than the typical size of the system. So I don't have to worry about incoherent processes. And this is the kind of system that I was telling you that it's not so easy to treat when you think about thermodynamics. Why? Because there are a very small number of electrons contained here. There are reservoirs in this too. There is alpha reservoir, beta reservoir, infinite electrons here, infinite electrons here. But at the coupling region, right, there are as many or a comparable number of electrons to the internal one. And this is a very arbitrary partition. I could say, well, the interaction will extend further inside or further outside. I don't know, right? So as soon as I have a problem where I have to define a partition, and the way you define the partition is very key for understanding, for obtaining the results, something is wrong. This is not a good approach, right? But this is the kind of problems we are dealing with. It's the strong coupling regime that is difficult for us. Okay, so sticking to quantum dots, I like this picture I showed very many times, right? I can define quantum dots in different ways, but here I like to classify them as wide open or closed, right? And when the systems are wide open, the opening here is large. And typically, if you measure the conductance, which is the inverse of the resistance, then and vary, for instance, the chemical potential or the external magnetic field, you see a funny pattern which looks a little bit like noise, but it's not. You can measure this repeatedly day after day, and you see the same thing. This funny shapes here, or this irregular, or shape has to do with quantum interference of the electrons that live inside this region, right? If I take the weak coupling regime and I almost decouple the electrons, the central region from the leads, what happens is that I go from a typical conductance like that to something that has very sharp peaks, which are almost equally spaced, right? And so why is that? And the answer is relatively simple, is that, well, if I have an isolated system and I want an electron to enter the system, it has to pay a price. This is a charged region, right? So all these electrons, they don't like to have another one here. So you have to pay a price, a charging energy. And once you pay this charging energy, then you are free to enter or to exit. And these are the regions where there is this resonance. And other than that, the process is blocked. So this is why it's called Coulomb blockade. Here, basically, since the entrance and exit are so wide, it's like when an electron wants to enter, it will push some other guys outside of the system, and that will be fine. It's almost like a liquid. And in between, there is a region where the physics is far more interesting and complicated from the electronic point of view. And I have very many experts in the audience. I won't go into these details, otherwise they will keep correcting my mistakes. I don't know enough about this. But this is the Kondo regime, where due to a combination of factors, there is a strong correlations that develop between the electrons in the leads and in the center of the system, and the transport is dominated by this kind of physics. So I had the pleasure to write a paper with Luis on that in the past, Luis Gregório, and Wernicke and George are big experts on that. Well, so this is the theoretical perspective, right? So from the point of electronic transport, this is trivial. This is almost trivial, and this is a little bit tricky. It's known already, but it's a little bit tricky. From the point of view of quantum thermodynamics, weak coupling is not a problem, right? And here, well, I don't know. The problem is here. From the perspective of quantum thermodynamics, this is the hard problem, okay? And so that's what we are going to stick at. So I'll address here a minimal problem on that. I'll consider, for instance, a system which is single level, and eventually the second class of problems I will address, there is a time dependence in the position of this level. I have left and right reservoirs, and there is a strong matrix element that couples my system to both reservoirs. And essentially, I can write this partition, which is standard, right? So I have an internal region. I can consider electron-electron interactions or not, right? This is the coupling, and this is the bed. And today, I'll drop this term. Sorry, George, sorry, Edson, but today I'm not going to discuss this. This problem has a long story here, actually, and in electronic transport and thermal transport. And so there are many people discussing over the years the system bath partition. And actually, I wrote a paper with Mariana, who is at Uberlândia, several years ago, where we show that from the electronic point of view, there is no ambiguity taking different partitions, right? A partition pre, any approach gives the same results, even for time-dependent transport. As far as for thermal transport, everything depends on the partition. And there is a paper which was actually exposes and puts this issue very precisely, and by Liliana Rachea, who I think she visited many times here, and these guys from Spain and Poland. And actually, they solve the problem being very democratic. They say, well, we'll take this partition and we'll put half of it in the system and half of it in the environment. And they claim that would be let's say a genuine way to solve this issue. And actually, they predict average quantities which kind of work well. The laws of thermodynamics are reproduced, but once you have more than one terminal, more than two terminals, then there are problems and ambiguities, and the fluctuations depend on your partition. This is very bad. So this is the problem. So the way out is to go back to one of the formulations of electronic transport, and instead of using non-equilibrium Green's functions, to go to Landauer-Büttiker. And the Landauer-Büttiker approach is one of the most successful approaches to electronic transport, and it assumes that the conductance is the same as transmission. And the transmission is something that you compute using quantum mechanics, right? So transmission coefficients, scattering matrices. Now, if you think about it, it's actually very nice, because when you study quantum mechanics, what you learn is that the transmission matrix, transition matrix, or the scattering matrix, they are formulated in terms of asymptotic states, right? So people when the theory was formulated, people were interested in what you measure at the detector, right? Which is very far from any quantum system, right? So people were thinking about nuclear scattering or atomic scattering, and the detector was way off. And so whatever happens in the interaction region, then the waves, they emanate, and eventually they are captured by the detector. In our problem, and that's the nice thing, in our problem, this is very nice, because you avoid, if you can formulate the theory in terms of the Landauer-Büttiker approach, you avoid entirely the issue of the coupling region. Why so? Because the Landauer-Büttiker approach assumes that you have a coherent phase propagation, and you measure the asymptotic states. And the asymptotic states are very far from this dangerous region where you have the coupling. So they take into account the system and the coupling, everything. And so you don't have this ambiguity on how you define the coupling region. Everything is already accounted for. And so the measurement actually, the Landauer-Büttiker theory is immediately connected to the measurement theory, and so there is no need for the coupling, right? If you can solve it, right? So that's the issue. And so this was our point of view, to formulate all this in terms of the Landauer-Büttiker approach. I'll drop this. And so let me tell you how it works for stationary problems, non-equilibrium stationary states, called also NES, when you apply a bias and the bias is fixed and the system doesn't change in time. So what would you expect from thermoelectrics? Basically, what you expect is that, well, this should be this should hold, right? And so if you inspect the entropy production, you take derivatives of all that, then the entropy production is related to the energy flow and the particle flow that exit the left and right contacts, and the balance is like that. So if you have a small the difference in temperature, then basically the entropy production should be related to the current, the charge current, right? The heat current, and here you have the particle current or the charge current, and this is what is expected naively, almost macroscopically. So there is no quantum here, right? You can do it a little bit better or more sophisticated using Onsager's formulations. And in linear response, you can actually define this L matrix, which contains all these coefficients that relate the forces to the responses. And then you can generalize what I already told you before, but you recover in the simple cases whatever we were discussing before. Okay, so now what can I formulate this in terms of quantum mechanics, right? And what is the entropy production in a beast like that? And in order to help us, I'll just present a quick argument based on one of the first papers on that. Entropy production as correlations between system and reservoirs. And these guys here we're studying a very simple model, very simple problem, where I have a system here, and I start with no correlations. All particles are here, or either here or here, and I let the system. I open this compartment, and I let the system evolve, and I study the entropy, the total entropy of the system, and by the end of the day, I'll see that there is an entropy production when I let the system evolve, which is related to this guy that is called relative entropy, right? Kullback, well, there is a name. People from quantum information like this name, but this is a relative entropy. So the idea is that there is an entanglement between the states at the system and the reservoir, and this entanglement is responsible for an entropy production. And I will show you that something similar happens in our problem. So how do I do that? I start with Landauer-Büttiker approach, so I'm a theorist, so there are equations after all, right? And if I write, for instance, a scattering wave propagating either at the left or at the right lead, this is the general expression for it. It can be propagating outwards or inwards, and I associate incoming electrons with A and outgoing electrons with B. I can write the current in terms of this field, and the current is a simple integration in transversal mode, and by the end of the day, the current is basically you count how many electrons enter the system and how many electrons exit the system, nothing else than that, by a certain rate. And all this integration makes this thing meaningful from the point of view of units, if you wish. So the scattering matrix relates the incoming electrons to the outgoing electrons, and by the end of the day, this horrible expression is the current in terms of these operators. And I got rid of the B's, introducing this S matrices, and this A's, they correspond to a matrix which connects incoming and outgoing electrons. Okay, actually, not a matrix. This is a product of matrices, and this is the general expression you find with Büttiker for many multi-probe terminals, if you wish. So, how this is related to what we are interested? Well, we have to take some average, right? So I'll get rid of the fluctuations. I take some expectation values, and I can write the current of the particle current in terms of some equilibrium distributions of the electrons in the lead A, alpha, and the lead alpha prime, and this transmission matrices. Very similar to what people have done, formulated modern formulation of the Landauer-Büttiker theory. Or sticking to a notation that I used in some of my papers, I can write also this as a function of this alpha phi out, which is a non-equilibrium distribution. So you inject equilibrium electrons, the electrons that get out, they are non-equilibrium. Okay. And so this is the current. And then the entropy production rate is basically this guy. You have the balance between the current, the heat current, energy current, and the particle current. And the entropy production is related to these quantities that I can compute using the Landauer formula. And a simple integration that involves the temperature of the reservoirs and the chemical potential of the reservoirs. Or I can write in this way. And so this is basically the theory for that. From that, I actually, what is nice is that if I consider just the case of a single channel, that's a simple exercise, I can show that the entropy production is related to this Kullback-Leibniz entropy or relative entropy, as the people from quantum information have shown for a system in equilibrium with a reservoir. And I get the very same result in a quantum dot, a single channel quantum dot. And I found this result very nice because it shows that our formula is consistent with people that with things that have been derived in quantum information without similar things in a similar situation, not really transport, but time evolution of a system which is strongly coupled. And this is what we have here. We have here, in addition, a drive, if you wish. But in linear response, this shouldn't be a problem. Okay, so this is reassuring, and this is our formula, right? So for the entropy production in a stationary state for a multi-terminal system. And we have been working on an extension to compute higher moments of the entropy production, which involve taking the average over higher moments of the current, taking the average of higher moments of this creation and annihilation operators. And we have been successful to go to a second moment and compute the noise. What information is in the noise? And this is a very nice thing. Well, I'll spare you from this algebra. It gave us some time for that. But the information which is contained in the noise is that you can immediately relate our findings to what people call thermodynamic uncertainty relations, right? And so there is a whole bunch of papers where people have noticed something which it's true also in small systems, classical even, that this relation should be fulfilled, right? So the variance of the current and related to the second moment and the entropy production -2 is greater than 0. This has been shown for a class of classical systems in this first PRL and has been extended to a wider class in the second PRL. So there is no general proof that this is true. And it's nice to check if this holds for quantum systems, right? And this is what we do here. And we take this very simple model of a single resonance, and this is a formula that you have seen many, many times. And with Alexandre Reilly Rocha, we computed this phi, and we find that if the system is weakly coupled, right, then you see that the law is not violated. This guy is always positive. But if the system is, this coupling gets stronger, right, then there are some interesting things that happen. So this guy here goes negative and then it increases again. And this is basically the bias. And so there is a 10 to the minus 2, is a small effect, right? And as the coupling goes even stronger, this correction becomes smaller to some extent, but it becomes quite a feature here. And we are still working on trying to understand the details of that. But so to say, this thermodynamic uncertain relations, they have a very limited applicability. And in particular, they are violated by quantum systems. Okay, so these are the results I had to report on stationary entropy production. Also, there are some experiments ongoing in Berlin at the von Humboldt University, and there are some interesting results also on non-equilibrium, right? Non-equilibrium, non-stationary. And since I don't have time, I just flash the setting for you, right? Now I can also remind you that there are no interactions, and I can actually pump the level up and down, right? And actually I can make the two reservoirs, put the two reservoirs equal, and by pumping the level up and down, I can actually produce a current. And depending on the magnitude of this pumping, this process is irreversible. Through a cycle, I accumulate charge, and this is what we do here. So this is a wrong paper. That research started in 2015. And it was actually Mariana who discussed this paper with us when she was still at UFI. And she brought it to our DICE seminar. Every week we discussed the paper. And she selected this one. And it looks very suspicious. And we were thinking about working on that. And the paper is actually wrong. It claims that you can use non-equilibrium Green's functions and equations of motions to derive all these results that we have derived using Landauer-Büttiker, but this paper depends on the partition, and there are several drawbacks in this approach. And that was the beginning of our research on this subject, by pumping electrons and thinking about the role of the coupling. And this is PRL I wrote 3 years ago on this subject. And the idea is, again, to write the S matrix for a process which is non-stationary. And so this approach contains an interesting thing, which is kind of new. It's the S matrix doesn't contain a single argument. Because when the electrons are injected in the system, they have a certain energy, but then the system is driven, and the electrons can increase their energy or can lose energy. So the S matrix has to contain two arguments, an argument which is the entrance energy, and the other is the exit energy. Or, if you wish, you can compute in something more which is perhaps more physical or is more palatable. The S matrix has two arguments. One is the entrance energy and the other is time, right? And here I go to energy domain. It's just a Fourier transform. This is advantageous when you compute all these corrections. And so this was the theory. So you can go on and you crank up the machine and you compute the S matrix using some adiabatic expansion, and you can compute the current, the entropy current, and thus the entropy production. And we applied this very successful for a number of examples, like the Thouless pump, and for a single level, you can actually derive all the results analytically. If you have more than one level, you have to do it numerically, actually. And so this is the conclusion. So if you pump a system, there is a reversible term. Some of the energy is dissipated, and basically, what is kind of neat in this formula is that this formula appears in one of these Barry's papers, where he was computing back action in adiabatic systems. And so there are lots of interesting connections in this physics, but unfortunately I won't have time to go into that. Okay, so the conclusions, to wrap up in time, is that the Landauer-Büttiker or Landauer-Büttiker-like approaches avoid partitions, the partition problem, and allows one to treat strongly coupled systems. As I explained to you, a strong coupling in the realm of quantum thermodynamics is a problem. And there is this inside-outside duality, meaning that by measuring things far away from the system, if the system propagates quantum coherently, then you can infer what happens inside. And by using this, you can actually recover standard thermoelectrics and standard thermodynamic relations for the mean, and you can actually make predictions for the fluctuations. And so that's it. So thank you very much for your attention, and I open for questions.
Thank you, Caio. Thank you very much. So, Luis is there already. He's very quick.
Yeah. No, I really enjoyed the talk, Caio. Very, very nice. I'm still puzzled by your point one there. I guess I'm not sure if I understand the problem with the partition, because if I understood correctly, you take the Landauer-Büttiker approach and you get an expression for the entropy productions in terms of a transmission matrix.
Yeah.
Now to calculate that transmission matrix, you have to get a model where there's some partition, right? And in fact, if you would do it via non-equilibrium Green's functions, you could get that transmission from Green's functions as well. So why doing through Green's functions doesn't work, and it works with Landauer-Büttiker?
Okay, that's an excellent question. So let me dwell a little bit more on that. That gives me an opportunity to show a slide that I skipped, and I hope this will actually. This is not my work, so this is why I skipped, but it's a good work. So these guys here. Sorry for the dog. So we have a dog here at home, and the dog barks every time there is a collector of the garbage. The dog likes to have the garbage inside, and I always tell the dog, look, the garbage goes outside. You should worry about people that enter the apartment, not people that leave, not things that leave. Okay. So, but the paper is a single terminal quantum dot, a minimal model, and it was written by some of my collaborators. This guy from Open, a student, and this guy is very bright guy, Nitzan. So, what they formulated is a very simple model, which is not transport, but it captures the physics that you are asking about, Luis. So suppose that I have a reservoir and I have a level here, and the electron is allowed to jump from the reservoir to the level and vice versa. And the level is pumped. I go up and down by some external gate, whatever. I drive the system, okay? So what these guys did is some very simple thing. They say, okay, let's try to write all the quantities I'm interested in terms of the driving velocity, of the time, of the speed that the quantum level goes up and down, okay? And so the zero order or equilibrium is trivial. So this is what you learn in the standard undergrad course, if you wish, right? So you write the grand potential, and from the grand potential you can extract all quantities you wish, and that's it. Now, if you go to the next order, right, the first order, it's quasi-statical, and this is the neat part. The next order is odd in the velocity, so that once you reverse, you undo all the main things. This is a reversible process, okay? And then you can, then you have to work a little bit harder, and then you start to invoke partitions, right? What is the reservoir? What is the quantum dot, etc., etc., and then you derive these guys, right? And the second order, which is irreversible, you can also compute the whole system and understand what's going on. Now, if you introduce the partition, and this is what I wanted to say, is that that's the nice part. If you approach the problem without thinking about currents, but the Landauer-Büttiker deals with currents, right? And here we are dealing with expectation values of energies, of heat, of things like that, right? And so the idea is that, for instance, if you look at this guy here, which is still reversible, it's a fun, nice object to look at, and I just single it out because it's a simple guy to look at. From the thermodynamic relations, there is no dispute, right? So that this is something that comes out from simple considerations. You can show that this guy is exactly this one, and everything, you know, like it's standard textbook. Now, if you want to go obtain this from a microscopic model using non-equilibrium Green's functions or equations of motion, then what you figure out is that this heat that is transferred to the system or extracted from the system, you have to compute the average bath energy with a half of the coupling. And so this is entirely arbitrary. And this is the only way you get the correct result. So in this sense, you have to find a way to play with the partition and to account for the partition properly, right? If you have a single contact, this is not ambiguous. But if you have more than one contact, two contacts, transport experiment, or many probe, then there is more, you know, there are many ways that you can recover results that you know what you should get. And for the fluctuations, you don't have a prediction because you have an ambiguity.
So you can always get the exact result from, say, Landauer-Büttiker and go back and figure out what the correct partition is. Perhaps.
That could be. But another way is that, okay, I use Negev to compute currents. But then it doesn't really make too much sense because then I use Landauer-Büttiker, right? Yeah. So the idea is that I want to avoid the partition, right? And the way you formulate the scattering matrix, and actually what you do is you're correct in saying that actually we do a partition when you do a scattering matrix, but this is only convenience because the results don't change. I just want to show this here. Suppose I take this dotted line, I extend the dotted lines, right? And I have to solve a central system which is big, very big. And I have the asymptotic states far away, right? From the quantum mechanical point of view, nothing will change, right? Because I'm not sensible to that, right? But obviously I don't want to do that because it's it's a nightmare. I take the smallest system I can, and I compute the quantum mechanics, and I get the S matrix from that. But the S matrix doesn't depend on the partition, and hence doesn't depend on the coupling.
I see. Very nice.
Okay,
Very
that's the idea. Sorry for the long answer, but
it was great. It was great.
Any more questions? Anyone? I see that Edson's there. Peter?
Yeah, nice talk, nice physics, Caio. And I am out of business for quite a time. But you showed very quickly this this slide with this experimental attempt in Berlin, correct, Humboldt?
yeah.
So the Landauer-Büttiker approach is a very nice one, and but do you have they have some control over the experiment if they are looking at asymptotic states?
Good question. This is a thing which always puzzled many people in the community about I mean, how far you need to go to be asymptotic, right? And I don't have a precise answer to that, right? But the idea is the following. So once you have your connection, let me rephrase. I'll tell you two things which are two different sides of the same thing. From the theoretical point of view, as long as you have some sort of constriction, right, and you compute an S matrix, right? Well, the chapter that is not contained in the undergrad physics, not even in the graduate physics course, is that S matrix has closed channels corresponding to evanescent waves. And these evanescent waves correspond to modes which are, due to energy, they are not allowed. And they propagate, then you feel only the tails of these states. In this sense, for us that we deal with constrictions, then we are almost sure that that you always capture only asymptotic states, because the others they die out very fast in size, right? When you move a little bit, they are gone, right? There is a long discussion in this book, which is not very popular, by Pierre Mello and this guy from India. I forgot his name. There is an appendix where he was always very puzzled by that, and he did a very thorough analytical discussion on this issue, and concludes what I said briefly in words. And he does it very elegantly. But you can also think about experiments, right? And in experiments, for instance, what is really nice is that, for instance, if you take the experiment where these things shouldn't really work so well, for instance, a quantum point contact, quantum point contact has almost zero length, right? It's just it's the smallest barrier you can think, the smallest hole you can drill in the systems. And nonetheless, except for some pathology at the first plateau, all the plateaus, they reflect perfectly well the number of open channels and asymptotic states that you have in the system. So in this sense, this is the experimental answer to the question, is that there is no evidence that you can capture something else than the asymptotic states. And from the analytical point of view, theoretical point of view, the best I can offer you is this simple-minded explanation. But if you're interested, that there is a thorough analysis in this in one of the appendix of this book. Oh, yeah, that's it. Yeah.
Fine, okay. So experiments are friendly to theory in this.
Yeah. Nature sometimes is kind to us, no?
Any more questions? I have, yeah, Edson, go ahead.
Okay, nice talk, Kai. Thank you very much. It's our pleasure to have you in our institute. Can you hear me well?
See, yeah.
Yeah, good. My question may be naive, but how difficult is can your life be, or how more difficult your life could be in a regime where the system is localized or non-ergodic? Is there any complication? At the beginning of your talk, you mentioned localization, thermalization. In this case, essentially you talk about non-equilibrium, but this non-equilibrium could be induced by some finite bias. But what about these localized states?
Localized states, yeah. Localized states. Yeah, that's a good question. I don't know. So the thing is that there are two main messages that I try to pass, right? So one is that you can measure the entropy production when you look at the currents that exit the system by applying a bias, right? The second message is that some of these things, they can be interpreted in terms of quantum information by the entanglement between the system and the reservoirs, if you wish. And so this transport process can actually lead to that. Now, if you have localized states, and these localized states lead to strong localization, then you don't have transport. and none of the ideas that I was discussing, at least the realm that I was discussing, is applicable. And more than that, if you're thinking about an insulator, then there shouldn't be really the entropy production, but more things like you should think about an isolated system that you prepare in a way, and you look at the time evolution. This is a problem which is very different than the one that I was addressing.
Okay, but it's still perhaps in the weak localized regime where the domain wall, for instance, could melt away, to still be able to measure how entropy cross some.
No, sure. I mean, these ideas you can apply to diffusive regimes as well, and stuff like that. I'm just saying that once you enter this dangerous localization, then
that is no more. That's right. Thank you.
It's a different stuff.
Right. You showed that slide. Very nice talk. Very nice talk. Thank you for accepting the invitation. You showed that slide that you had a strong coupling, intermediate coupling, and weak coupling with condor in the center, but I don't really want to talk. Yeah, I don't want to talk about the condor. In the what you say, the wide open, and you show all these fluctuations in the conductance, and that is the hard system to treat. But it came to my mind that if I am talking about conductance and I have a topological system like the quantum Hall, then in reality, I have a very so good the value that you get for the conductance that it's used as a standard, right? To define the standard for conductance. But a quantum Hall bar is still a macroscopic system, right?
Yeah.
Let's say. Do you think that making it smaller and smaller and smaller, you would get to a point where the topological protection would vanish and you would get this kind of fluctuations? Or that system would be interesting to study because it wouldn't do that? That would be my question.
Well, we're talking about a different physics regime, right? So
yeah.
So
but it's still wide open, right?
I understand. So it's a different kind of system. Is definitely a system people are interested in nowadays. It's wide open, but we know that all transport is chiral. It's edge states due to edge states.
Okay.
And the conductance is perfectly quantized. In this sense, actually, it's an interesting question because there is a whole bunch of dispute on dissipation-less transports in for instance, in topological insulators, and this is a subject which is slightly more controversial than what I say here, and you can apply the formalism I used here, which is for non-equilibrium stationary states and safely for quantum Hall, etc. But the fluctuations won't be there. And you are right. If you make the system smaller and smaller, then you lose this protection, and the system becomes more boring in a sense, or usual, right? Because then you can intercommunicate between opposite edges, and the system is no longer quantized. But I want to draw the attention to everybody that there are some people interested in measuring what they call equilibrium currents in these kinds of systems. And this is a very complicated from the experimental point of view. So there are a number of few recent nature physics and science papers, and it's still a little bit controversial from the theoretical point of view, because this is equilibrium currents is not Landauer-Büttiker, it's not conductance, it's conductivity. It's a property of the ground state, of the many-body state. And this is a subject, you can invite Leandro Lima to give a talk on that.
Leandro Lima, where is he from?
He wrote a paper on that, okay? So he was my former postdoc, and there is a lot of dispute on this.
Where is he now?
At the Universidade Federal Rural do Rio de Janeiro. UFRJ with two double R.
Okay. I'm gonna look for him.
My alma mater.
Yeah, alma mater of exactly.
Yeah. That's exactly what I thought. Yeah. Okay. So, any more questions? Edson? No. So
Eduardo was here. I wrote.
Eduardo left, and he left, and he said, "Great talk."
No, I wrote most of the papers on conductance fluctuations of my career with Eduardo.
Okay, okay, okay.
Yeah, you wrote here. Adrian Feguin is around too.
Adrian Feguin is there, yeah. Hi, Adrian. Maybe he's...
Yeah.
So if there are no more questions, we should thank the speaker again. Very nice talk. Thank you very much. And you know that you last but not least, you were our last talk of the semester. Adrian is typing. He probably doesn't have a camera or